Welcome back. It's Tim Undorf with Midwest Laboratories. We're going to start part 3 here of interpreting soil analysis. In the first two parts, we looked at organic matter, cation exchange capacity, pH, and buffer index. We also looked at phosphorus, potassium, magnesium, calcium from the part per million standpoint. We also looked at those cations on the base percentage standpoint, those ratios of the different cations to each other. So today we're going to look at nitrates, sulfur, zinc, and the other micronutrients. So in the first two recordings we checked the top half of the report. Now we're going to move down here to the bottom half of the report. So let's start off with nitrate N. One thing to keep in mind when you're looking at the nitrate N analysis from Midwest Labs on the soil test reports is this is just measuring nitrate. We're not looking at any other types of nitrogen in the soil. Now nitrate, of course, is the very available form of nitrogen that most plants are going to take up through the growing season. It's generally that final conversion from either organic sources of nitrogen or fertilizer sources of nitrogen. They're going to convert through to ammonia and eventually to nitrate. At that point, it's going to show up on our test results. If for some reason say the fertilizer you had applied or even some of the organic nitrogen that's breaking down is still in the ammonia form, that will not show up on this test. So one thing with a lot of the nitrification inhibitors that are out there that people are applying with their nitrogen fertilizer, that could keep ammonia-based fertilizers in the ammonia form and stop that conversion to nitrate, or at least delay that conversion to nitrate, so that maybe we wouldn't find that fertilizer on this test result. If you know you've used a nitrification inhibitor and you think that that might be a cause for some of the nitrogen that you've applied to not have converted to nitrate yet, you might want to check for ammonia as well as nitrate. We did not do that on this test result on any of these samples, but that might be something that you would want to consider. The other form of nitrogen that's often out in the soil, of course, is organic nitrogen, and it actually is in the soil in much larger amounts than either nitrate or ammonia in most cases. The organic form, of course, has to mineralize to a mineral form, either ammonia or nitrate, to be taken up by plants. So the organic form of nitrogen in the soil is very important, but a lot of times it's a little irrelevant to the plants in that growing season because a lot of it is not going to mineralize during the growing season. We do get producers or agronomists occasionally asking us for total nitrogen in the soil. That's a number that we certainly can measure, but it's often a confusing number and doesn't correlate very well back to yield because the majority of that total nitrogen in the soil is in the organic form. It could be as much as 500, 1,000, or even more pounds to the acre, but those pounds are not available to the plant, so they're really irrelevant to the nitrogen fertilizer recommendation, or at least they're very difficult to interpret. So with that said, let's look at these results here. We only have nitrate results on 4 of the samples. Some of these samples were grid samples, so a lot of guys that are doing grid sampling don't look at the nitrates in those. They're also shallow samples, of course, so the nitrate number in a shallow sample might have a little less relevance to the nitrogen available to a crop than what a deeper sample might. So a lot of times when people are looking to assess soil nitrates, we'll ask them to take deeper samples. The pre-side dress nitrate test that was developed by several of the land-grant universities. I know it's used heavily by Iowa State, but I want to say some of the eastern universities push it as well. That's a 1 foot deep sample, so 0 to 12 inches. Some of the land-grant universities will talk about looking at carryover nitrates in a 0 to 24 inch sample or a 0 to 36 inch sample. Those are really decisions for you and your agronomist to make together to decide on how deep you want to look at nitrates, and of course a lot of that's going to have to do with how deep you think those crop roots are going to be able to go to assess or access that nitrogen in the soil, those nitrates in the soil. So we have the 4 test results here. We've got a 29 part per million in a 0 to 6 inch sample. We've got a 14 part per million in a 0 to 8 inch sample, a 7 part per million, and a 12 part per million, also 0 to 8 inch samples. And these are coming from that eastern Nebraska soil, the western Nebraska soil, and the 2 eastern South Dakota soils that we're seeing those numbers on. Here at the laboratory, we're going to give you those results in 2 different ways. We'll give you the results in part per million, and then we will make a mathematical conversion from part per million to pounds per acre based off the depth that you give us that you pulled the sample at. So that's one key thing we'll see here, as this 29 part per million sample in the sample from eastern Nebraska has 52, or converts to 52 pounds per acre of nitrogen. You would think that this 14 part per million in this sample from western Nebraska would convert over to a number that would be more than, or I should say less than, half the number coming from the 29 part per million that you see here. The difference in that math is this is a deeper sample. So when you take that part per million and you convert it to pounds per acre with the deeper sample, it's going to have a larger impact in total pounds per acre. The conversion that we use is basically the part per million times the depth in sample in inches times 0.3, and that's going to equal out our pounds per acre. So a deeper sample with a lower part per million might actually have a higher pound per total acre because there's more total soil mass represented in that sample. So that's something to keep in mind. If you send us multiple depths, they'll be broken out here in subsoil 1 and subsoil 2, and then for each of those depths, of course, we'll have a range here. We'll use that for the conversion of part per million over to pounds per acre. Each depth will get a separate test. The test will give us results in part per million, and then we'll use the depth that you give us to calculate out the pounds per acre. And then over here to the right of the nitrate results, we give that total pounds per acre, and that's going to be a summation of the different depths. In this case, we only have the 1 depth per set of samples. Oftentimes growers or their consultants will pull subsoils, and then those subsoil depths will be used to add on additional amounts of nitrate for that total pounds per acre. So that, in a nutshell, is the nitrate analysis. Not a lot of confusion there, but hopefully you do keep in mind, if you are using nitrification inhibitors and you're checking that available nitrogen in the soil, maybe early in the growing season, where those nitrification inhibitors have not allowed that conversion of ammonia to nitrate to happen yet, that you might want to check for ammonia as well. Okay, let's move on to sulfur. So the sulfur analysis we're going to do with any samples that are requested as part of one of the more in-depth packages. So what we showed you there on the top would be all part of our S1A package, with the exception of sodium and the percent sodium base saturation. That's generally going to be an add-on test. And then everything here in the bottom half of the soil reports are add-on tests. So from a sulfur standpoint, at the laboratory, we usually use the part per million of sulfur to make our sulfur recommendations. Some people will use percent organic matter either to make their sulfur recommendations or to adjust their sulfur recommendations. We don't here at the lab, but I certainly am open to that line of thinking. The idea is the higher the organic matter in the soil, the more sulfur is going to release through the growing season, and that should be part of the overall sulfur recommendation. At the lab, since we're not looking at percent organic matter and we're just looking at the sulfur content in the soil at the time the sample was taken, we're kind of setting a target of around 20 to 25 part per million is about where we want to be. If we're lower than that, we're going to be making a sulfur recommendation. That recommendation that we make is going to be adjusted for yield. Generally, it's going to be around a pound of sulfur for every part per million. It's short of that target within an adjustment made for yield. But again, I'm not here to make your recommendations for you. I'm just kind of trying to walk you through the numbers that we're looking for and how we react to those numbers when they're lower than what we're shooting for. So as you looked here, a lot of these samples, we probably make a recommendation for applying some additional sulfur. You might argue that with nearly 3% organic matter, some of these samples would probably provide some of that sulfur on their own. You could probably go either way. We've got some higher organic matters here at the central Iowa and eastern Nebraska samples. In that central Iowa one, we also have some pretty high sulfur numbers. So in that case, we may not make much of a sulfur recommendation. Another thing that you should think about as you're looking at whether or not to make a sulfur recommendation might be how early in the growing season you're going to, say, plant your crop, or if you're talking about a cool season crop. Of course, when you're relying on mineralization of the organic matter, that's going to require some warmer temperatures. So you might err a little bit more to applying sulfur if you're planting early or you're dealing with a cool season crop. So a couple things to think about. As we walk through these samples, like I said, the first three here, the 3 western Iowa samples, we'd probably make a recommendation on. This central Iowa sample at 22 part per million, fairly high values, so we might back off on making a rec there. The 11 and 17 part per million that we see in the eastern Nebraska and the northeast Nebraska samples, we'd probably make a recommendation on. Another thing to consider from a sulfur standpoint is you're looking at this northeast Nebraska sample. Very low organic matter with less than 1%. We've got 17 part per million sulfur, but we also have a very light soil with a lot of sand in it because of this. We see that with this cation exchange capacity of only 6 or 5.8. We know a soil like that's going to have a hard time retaining sulfur. We also know water is going to flow through a soil like that fairly quickly in most cases. So we'd be worried about retention of that sulfur, which is a fairly mobile nutrient in the soil. So we'd probably look at maybe doing some spoon feeding there, maybe applying sulfur, say in the fall or early spring. Might not be as good of an idea as maybe making an in-season application with a soil that's not going to hold the nutrient and is going to have water leaching through it rather rapidly. So those are some things to think about. As we get down to the western Nebraska soil, we see a fairly high sulfur value of 29. We probably would hold off on making a rec on that. Again, I think every grower's got to think through their yield expectations, and again, because sulfur is a mobile nutrient, they might think a little bit about some in-season application, especially if they're doing in-season application of nitrogen as well. On these last two samples, here we come up with a very high sulfur number, this 72 part per million. So anytime I see sulfur values over about 25 part per million, I really have to ask myself why. In the case of this eastern South Dakota sample, it could be that we have poor drainage here. Like I said before, sulfur is a very mobile nutrient, maybe not quite as mobile as, say, nitrate in the soil, but still fairly mobile. If it builds up in the soil, it's generally telling you that water's having a hard time at infiltrating and percolating through the soil, because if it were moving normally, it would probably pull that sulfur out of there. The other thing that could be happening is if the drainage is fine, and that's not the explanation, a lot of times high sulfur values will come from an amendment being applied that contains sulfur. And one that often would be applied that would contain high values of sulfur, especially if it's applied at high amounts, would be gypsum. And we talked back in, I think we were talking in video 2 about those high % magnesium base saturations in these last two soils. And we mentioned that gypsum might be a way that a grower or an agronomist would try to lower those magnesium percentages and build up his calcium base saturations. If that gypsum amendment had been applied with the intent of trying to accomplish that, it would very likely push these sulfur part per millions quite high. So that might be your explanation as well. And then the last sample here at 16 part per million, again, would probably make a recommendation for that one. This high sulfur value brings up a good point that really should be brought up for the entire nutrient values and all of your soil test values, whether you're looking at cation exchange capacity, pH, phosphorus, potassium, any of the nutrients. When you find outliers like this, you really should put some thought into why that outlier exists. Now in this case, with our very high sulfur number, it might be that we've done a past gypsum application. It might be that the field has drainage issues. It might be that there's high sulfur in the irrigation water, and that's leading to high sulfur in the soil test values. But you need to think through why that is and be able to explain it and understand it, because it may affect your decisions that you make off of these numbers. The same thing would be the case. We talked about this back when we were talking about phosphorus, these very high phosphorus values of 99 and 129 part per million that look like maybe they were due to some manure application, especially when we combine it with this zinc value in this central Iowa soil at nearly 12 part per million. If you can explain that because you understand that maybe a feedlot used to be or an old building site used to be where that sample was pulled, or maybe you know that area of the field has gotten high manure application in the past, maybe it was close to the feed yard, maybe it was close to the hog barn, then there's your explanation, and these numbers are valid, and you should probably go ahead and make your fertilizer application according to what these numbers tell you because they make sense. If that's not the case, if there was never a building site or an old feedlot where this sample was pulled, if there's never been a history of high levels of manure application where the sample was pulled, then maybe the explanation is different than that. Maybe last year you had stock cows out on this field, and where you happened to pull this sample was either where the bale ring was located or just happened to be where a cow relieved herself. And that's why you've got very high numbers there. If that is the case, it probably doesn't make sense to use that sample to set the fertilizer application or the recommendation for, say, an entire field or an entire zone, or maybe not even an entire grid. So if values like that come back that don't make sense, what you may want to do is go back out there and pull another sample. You probably got into an area with some very high values. That can also happen with banded fertilizer. If you're doing strip till or maybe some type of a starter fertilizer, a 2x2 with fairly high rates, you can come back with some very high values if you get one of those cores coming out of that fertilizer band. And those values are not appropriate for making a fertilizer recommendation if they don't make sense. So it probably would be best if you went out and pulled that sample a second time. Let's say you grid sampled that field, and this is just one value in a grid sampled field, and the value doesn't make sense for that area. There was never, a high manure application. Maybe there was some strip tilling done, maybe there were some stock cows out there, and you know that this soil test value is an anomaly. It's not a value that you want to make fertilizer recommendations off. Then what I would tell you to do, if you don't want to spend the time to go out there and pull that georeference sample again, then I would go into that data set, maybe flip it into a spreadsheet, and adjust that number to match the numbers around it. So I'd probably put it on the high end of the surrounding samples around it because it is a very high value in this case with the 99 part per million phosphorus and the 12 part per million zinc. But if I don't have a valid explanation for why that number's high, and I know that this is bad data, test coming back from the laboratory, correct? We check it twice, especially on this phosphorus, with the 99 part per million on the P1 Bray and the 129 part per million coming back from the P2. We're confident and comfortable with those values, but maybe you know that that value is probably just the case where that probe happened to pull the sample from. It would probably make sense to take the average of the samples around it in a grid sample scenario and replace these numbers with an average number for those values, or maybe the highest number of the values right around it. So that's where the art kind of comes in maybe and takes over from the science a little bit. So it might be something you want to, if you're a grower, to talk through with your agronomist. If you're an agronomist, again, you certainly want to be transparent about what you're doing and have a conversation with the grower so you can understand whether or not it makes sense that these numbers would be valid, and if they don't, maybe you want to make some sort of an adjustment or put in some sort of a minimum application so it's not making no recommendation based off these very high test values when they're probably not appropriate for the entire area that sample is representing. So hopefully that makes sense to you. All right, from there, let's move on to zinc. So from a zinc standpoint, and we'll talk through all the micronutrients, let's start with zinc. It's probably the one that we see being checked most often here at the laboratory, especially in say, a corn, soybean scenario. A lot of people raising corn are checking zinc values in the soil, but it's also the case for other crops as well. What we like to see on the zinc test is a number around 2 part per million. Somewhere in that 1.5 to 2 part per million is probably a pretty good number for most soils and most crops. Of course, if you're growing a crop that's maybe a little different than the average production crops, corn, soybean, wheat, alfalfa, you might want to check with that crop specifically. But here at the laboratory, for most crops, we're looking for a number around 1.5 to 2 part per million. So we see here as we look at samples 1, 2, and 3 through western Iowa, they're all a little low. All of them should probably get a zinc recommendation. One thing I would bring your attention to is sample number 2 here from western Iowa. We've got very low phosphorus values at 10 part per million and very low zinc values at only 0.4 part per million. Sometimes in some soils and with some crops, this interaction between phosphorus and zinc could actually drive a zinc deficiency. If you were to make a very large phosphorus application, which this 10 part per million is going to be calling for, and did not make any zinc application, you might push a zinc deficiency into that crop where normally it might have just enough to get by. In this case, with putting that very high amount of phosphorus down, you might push that deficiency in the plant. So I would recommend for growers or agronomists who see a very low testing zinc as well as a very low or low testing phosphorus value that they hold a little money back as they're making their phosphorus recommendation, and make sure they cover a little zinc as well so that they don't drive that zinc deficiency and then basically hamstring themselves from the benefit that they were hoping to get from applying that phosphorus by making zinc now the limiting factor in the crop instead of phosphorus. So something to think about as you're looking at soils that are very low in fertility in general. If you're pushing a lot of phosphorus at it to try to raise those phosphorus soil test values, you might want to make sure you hold a little money back to make sure you can cover a little zinc on there as well. So the top 3 samples, we'd be making a recommendation for zinc. And again, as we talk about recommendations, you've got to prioritize for your crop. So you've got to know for your crop what the most likely limiting factors are. Say for corn, I would say nitrogen's probably number 1. A very acidic pH, if that's the case, would be number 2 for a limiting factor. Phosphorus is oftentimes number 3. Potassium usually is going to be number 4. Sulfur and zinc will follow right behind that. Now that's going to be different for each soil depending on where your soil is. If you have an extremely low level of any one thing, it might move to the front of the line as the limiting factor. But generally speaking, on an average soil with an average yield goal for corn, I'd kind of walk through that priority list: nitrogen, pH, phosphorus, potassium, sulfur, zinc. But again, you've got to know those priorities and what the most likely limiting factors are for the crop that you're dealing with. So again, back to zinc. Sample number 4 here, we talked about already, there's a lot of zinc there. If that is truly representative of that area, if it's gotten a lot of manure application in the past, maybe it's actually an old building site or an old feedlot, and you can separate that area off and treat it differently, then yeah, it wouldn't call for any additional zinc. If you know that that's not truly representative of the entire area that you are trying to represent with that soil sample, then you should probably go out and pull another sample. Or, like I say, if you've got a lot of data around it, like in a grid sampling scenario, you could go ahead and just adjust the number to match the average of the samples around it. But again, that's where the art comes in versus the science. Don't just jump into that as an amateur. Your best bet is to go back in and pull another sample if you're not sure. All right, our 5th sample down here, this is the one that came from eastern Nebraska. Again, this is a field with pretty high fertility. We knew that going in. High organic matter, 61 on the P1, 117 on the P2, a good balance there, that 1-to-2 ratio, but very high fertility across the board. We knew it had high potassium numbers. So this one most likely has gotten good fertility in the past. In this case, it looks like they covered the zinc as well with a 3.9 part per million on the zinc. We talked about extracts and methods earlier on some of the other videos. I will say for the micronutrients, you see here DTPA, that's the extract solution that we're using for all these micronutrients. So that's something to keep in mind. If you see test results from other laboratories that you're trying to compare to, you want to keep in mind if they're using something like, say, the Malick 3 method, those numbers can be a little bit different. The same would be true of phosphorus. If they're using the Malick 3 method, you may see a little bit different values than what you would on the P1 Bray, P2 Bray, and certainly the Olsen test as well. So keep in mind you need to look for ratings for the method you're using and understand how your soil test values stand in those rating systems, and your land-grant universities are a great place to go to find those ratings. The agronomy handbook that I referenced in video number 1 would also be a good place where you could find those ratings for different soil test methods. So here on the 6th sample down, this is going to be that northeast Nebraska sample. We knew very light sample, sandy, or very light soil, sandy soil, low CECs, fairly low fertility with the exception of potassium, low organic matter, and we're low on zinc here as well. So I'd certainly be making a zinc recommendation in that one. And that goes back to, sandy soils versus heavier soils. You probably should expect to be making recommendations for more nutrients on sandy soils because they're just less likely to hold them. And since they burn through the organic matter quicker because of the larger pore space and generally a little better aeration, often they have lower organic matter percentages and aren't able to supply some of those nutrients through organic matter like a heavier soil might be able to. Alright, so we get into this western Nebraska soil. Again, we're above 2 part per million zinc, so probably not a recommendation here from our side. If you want to put a little zinc in a starter, especially if you're doing some early planting dates and you want that zinc, which, corn and zinc kind of seem to go together. If you want that zinc in a starter fertilizer, you might still make a recommendation for the starter, but no reason to build soil test values from our standpoint anyway. And again, we might make a little adjustment based on a very high yield goal, but for an average yield goal, this 2 part per million we think would be fine. And then these last 2 soils from eastern South Dakota, a little below those targets I gave you, so we really wanted to be at least at 1.5. We preferred more like around 2 part per million. We would make a zinc recommendation in this case as well. And as far as the amount of zinc we would recommend, I'll kind of leave that between the grower and their agronomist and the products that you're looking at. It varies a lot. If you're using a broadcast zinc product like a zinc sulfate and you're trying to build the overall soil test values, we're going to have a higher rec than if you're using something that maybe you're applying in a band, like in a starter, like a chelated zinc. Those are just 2 completely different recommendations, so I'm not going to really go into that in this video. All right, let's move on to the other micronutrients. We covered some that, the zinc, which a lot of people look at. Of course, we covered sulfur, which is more of a, mid-level nutrient, not a micronutrient. It's one that a lot of people look at, and the plant uses in fairly high pounds per acre compared to zinc and the other micronutrients. But moving on to manganese, we're basically looking for a number somewhere around 12 part per million, 10 to 15 part per million. We'd like to be in that range. We can see here that only on some of these samples did we do the full analysis and get all the micronutrients. So from a manganese standpoint, that western Iowa soil, sample number 3, we're pretty low. So we'd probably be making a recommendation for a little bit of manganese application. It wouldn't be a very high amount, it'd be fairly small. On the sample number, this is going to be sample number 5, so this is that central Iowa, no, the eastern Nebraska sample. 8 part per million here, again well below our 12 part per million that we're shooting for, so we would have a little bit of a manganese recommendation. You can see here on this soil, it's got high zinc, high phosphorus, high potassium. My guess is in the past the grower's been paying a lot of attention to those things, but maybe hasn't looked at the other micronutrients that much, and we see this low manganese value. Again, manganese is one of those things that can be kind of difficult to build the soil test values because the recommendation is going to be small. The next time you go out there with a probe, you may or may not get the area where the fertilizer hit. You may decide to meet these needs with some sort of a micronutrient starter type banded product, or maybe you're looking more like thinking about a foliar type product and you're just using the soil test to confirm whether or not you think you might need to apply something. Again, that's all a conversation that should be between the grower, the agronomist, and their fertilizer supplier. I don't really want to delve into that too much as far as giving you advice here from a laboratory standpoint, because I don't know your farm. I don't know what application methods you're normally using or what products you have access to. So again, I'm just telling you that from our laboratory standpoint, we'd be making a recommendation here. When you get a recommendation back from the laboratory, we're generally looking at a broadcast application. So if you're going to be banding a product, whether it's zinc or manganese or copper or iron, you might lower those values and not apply as much as what we're calling for in our recommendation, because again, our recommendations are based off of a broadcast application. All right, let's move on to the other samples here. We see the 3 part per million here on this western Nebraska sample. Boy, that number's sure awful low, right? So it looks like we'd definitely be making a recommendation. Here's where you go back to, you need to think through the total soil test and not just these individual analysis. In this case of manganese, this 3 part per million could very well be related to this very high soil pH. So a soil pH of 8.3 looks like it's still allowing a lot of zinc to be out there fairly available to the plants, but manganese may very well be being tied up by this soil pH. So making a soil application of manganese with a very high pH like this may or may not make sense. You may decide that you want to deliver that manganese more through something that's banded to try to limit the tie-up in that high pH soil, or you may look at some sort of a foliar application. Again, something to be discussed further with your fertilizer suppliers and your agronomists, but something you're going to want to think through is when you have very low soil test values of some of these micronutrients in a high pH environment, putting them down in the soil may not get them available to the plant like you need them to be. Then our last 2 samples here, actually fairly high, these eastern South Dakota samples. So in this case, we probably would not make a recommendation for additional manganese to be applied. One other caution I want to throw out there with manganese. There is the possibility of manganese toxicity. Now, generally, if that's going to be an issue, you'll see those very high values already in the soil test report. I really wouldn't consider a 16 and a 17 high enough to be a toxicity issue. Generally, they're going to be much higher than that. But the warning I'll throw out there is be careful of applying additional manganese in soils with very low pH. That very low pH a lot of times will push a lot of manganese available that wouldn't normally be available in the soil and can lead to toxicity issues. Generally only happens at pHs that are below, say, a 5.2, more often in the 4s. Oftentimes it's going to be combined or combined with aluminum toxicity in the soil. So something to be aware of. If I had a very low pH soil, say in that 5.2 to 4.8 range, I would lime to correct the acidity before I worried too much about manganese, because I'd be concerned that throwing additional manganese out there may create a toxicity issue. But that's tough to tell, and you really don't know until you do some plant analysis and look at the uptake of that nutrient in those plants to see if you truly have a toxicity issue. But I'd be careful in low pH environments. All right, enough about manganese. Let's move on to iron. For iron, we're looking at a target of maybe 20 to 25 part per million. Above that, there's probably plenty of iron in the soil. Below that, we may be having some issues. So as we look through these samples, and in generally what I find in a lot of Midwestern soils is there's plenty of iron there. There's probably actually a lot more iron in the soil than what we see here in the DTPA extraction. But of course, we're always looking at what those extractions bring out in nutrients, not the total amounts in the soil. So here again, looking at this DTPA extract, we're looking for a target of about 20 part per million iron. Most of these samples are well above that. The one exception is, again, our high pH soil from western Nebraska. We're at an 8.3 pH. That seems to be affecting the availability of manganese as well as iron. So we might be making a recommendation for both of these nutrients. Again, as you go to throw those out into the soil in some sort of a broadcast, those may tie up on you and not be available to the plant. So you may want to think of some other way to deliver those nutrients to the plant. And again, our last 2 samples here, very high levels, so would not have a recommendation for iron, but worth checking. What I usually tell people on micronutrients, let's just say that you're grid sampling your fields. Well, you don't want to pay for the full micronutrient analysis on all those different grid points. So instead, maybe what you'll do is 1 sample out of 5 or 1 sample out of 10, you'll check for micronutrients so that you know what your levels are. If you're doing a plant tissue testing program, then I would recommend that you take a few more soil samples, and maybe take a soil sample at the time that you take the plant tissue sample, so you know that the 2 are correlated together, that the plants that you're taking the leaves from, you have soil from that same area to check. My plant tissue values, is that issue a uptake issue, or is it a lack of nutrients in the soil issue? And you really don't know without a soil test to look at. So that's what I would tell you about micronutrients. You don't necessarily need to take them with the same intensity that you would on, say, a phosphorus or a potassium or pH or sulfur or zinc that you're planning on doing variable rate application on. If you're planning on just a blanket application for those other nutrients, you might look at just taking a few of them across a field or on a zone base. But in the same respect, if you're looking at going into a full-blown combination of soil and plant tissue analysis, and you're really pursuing high yields, then it might make sense to make sure you've got those georeference samples with the micronutrients in them, so that when you get your plant tissue samples back, you can look and see what those soil samples were taken from areas close to that plant sample, what those micronutrient values are. So two ways of thinking about that. Kind of up for you, the grower and the agronomist, to decide how you best want to spend your money on the laboratory analysis. So moving into copper, basically we're looking for around 1 part per million. Most all of these samples have that. There again is the one exception, the high pH soil. Again, I would say copper most likely is being tied up by that high pH, so it's limiting its availability to the plants, and that's what we're seeing here in the DTPA extract copper. So again, you might want to consider how you would apply that to avoid some of the tie-up that looks like is going to happen when you put it into that soil. So how you deliver that copper, you might move more towards something that's banded or something that's going to go through a foliar application. And then the last micronutrient we're going to look at, of course, is boron. So boron is one that gets quite a bit of emphasis, especially in the trade area that I cover. So the number we're looking for on boron is somewhere around 0.8 to 1 part per million, maybe 1.5 part per million. Certainly above 1 part per million we're pretty comfortable with. 0.8 is kind of on the edge. If you're under 0.8, we're most likely going to be making a recommendation for boron. One caution with boron: there are toxicity issues with a lot of boron fertilizers and the seed. So it's one that you should be very careful about putting in a starter fertilizer. I would definitely talk to my fertilizer supplier, and they would have to have complete confidence that that product was seed safe before I would put it in a starter. I would keep boron out of a starter for the most part. Also, if you look at banding boron in a strip till or maybe in a 2x2, you can create a toxicity area by banding that boron. So the recommendation that comes from the laboratory, like I said earlier, is based off of broadcast application. If you go to band boron, you really should reduce that recommendation by 10. So divide it by 10 to come up with an appropriate recommendation for a banded application. The recommendation for boron, again, from the laboratory is based off broadcast application. If you're going to band it, again, banding it with the seed is probably not acceptable at all. If you're going to band it some other way, say strip till or a 2x2, then you divide that recommendation by 10 to avoid putting some sort of a toxic boron band in the soil that may have some negative impact on that crop. So I'm real careful with boron. But it is a nutrient, especially with crops like, say, alfalfa, that can be limiting. So I'm not saying that you should completely ignore boron or never make application. It's just you've got to be careful on what you're doing. A lot of people will go with some sort of a foliar product to avoid that issue with the toxicity. Again, work with your agronomist, work with your fertilizer supplier to find the right product for the crop that you're using that's going to avoid any of those toxicity issues. All right, so that covers our micronutrients that we're pulling there with that DTPA extract. The laboratory will do some other micronutrients if asked. We can do chloride that's asked for quite a little bit, but it's a separate test that you'd have to ask for separately. These are the ones that we're asked for most often. We have 2 more test results to go over here. Excess lime. So excess lime is a test where we're basically looking at what happens with that soil if we were to add a strong acid to that soil. Does it have a lot of reaction, or is the reaction fairly low? In this case, we've got 2 samples where we did it for, and we do this on the complete analysis. So the sample from, this is eastern Nebraska with the good high fertility, had a fairly neutral pH, if I remember right. Yeah, slightly acidic, pH of 6.4. I would not expect that soil to react very strongly to an acid being added to it. And that's what we see here, low excess lime. So basically, again, we're adding an acid to that soil and we're looking at the reaction. If the soil has a lot of excess lime in it, there'll be a strong reaction with that acid, a lot of fizzing, and that's what we'll report on the soil test report. And that's what we see here with this second sample where we ran the excess lime analysis. This sample had a very high pH. This again is our western Nebraska sample with the 8.3 pH. There is, it looks like, quite a bit of excess lime in that sample because when we add an acid to it, there's a strong reaction. That indicates that there's probably some free calcium carbonate out there, and we should be aware of that because that gives us some of the same issues that we saw with the micronutrients. It's a lot more likely that that soil might tie up nutrients that are applied to it, including phosphorus, and we saw that with what we saw here from the Olson, the P2 Bray, and the P1 Bray, and looking at that when we used an extract that was caustic instead of acidic, we actually saw higher phosphorus values. Again, it's because that soil was neutralizing our extract solution. So this is telling us to be a little careful with applied nutrients. It's highly likely that they would tie up, so think about doing some banding maybe to limit that tie up. And again, like I talked about with the boron, be very careful about creating a toxic band by using the broadcast application recommendation that would come from the lab and then trying to make that same application in some sort of a banded application. All right, last but not least, soluble salts. So soluble salts are part of our complete analysis. Here we're looking at the salinity of the soil. When we measure sodium, we're looking at the level of sodium in the soil, or is that soil a sodic soil? In this case, this soil has quite a bit of sodium in it. It doesn't truly meet the definition of a sodic soil, which would probably be a percent sodium, much more like 10 or 15% sodium. A saline soil has a lot of overall salts in it, not just sodium, but all potential salts. And what this really is going to tell you is, can that plant fairly easily pull water from that soil? Now, of course, you can have issues like compaction or a drought that's going to make it difficult to pull water from the soil, but those would be compounded by a soil that had a lot of salinity, and maybe even in conditions that were fairly optimal for plant growth otherwise, a decent soil with a good mix of air and water in its pore spaces and without a lot of compacted layers. If it had a lot of salinity, those plants a lot of times will still have a hard time pulling water from that soil because those salts are pulling against the plant and trying to pull those waters to themselves. So it's basically called osmotic pressure, and the plant has to work against that to pull water from the soil in a soil with a lot of salts in it. Generally, when I'm looking at these soluble salts, kind of the number I use a lot is, say, a 0.7 to 0.8 is kind of my line where I would say soils below that really don't have a lot of salinity. Soils above that have increasing levels of salinity. As I get above a 0.9 to a 1, I'm going to be concerned about the salinity of that soil. And if I move above a 1 to, say, a 1.5 or a 2, you might really start to look at salt-tolerant plants. And that's really beyond the scope of this presentation, but you can go onto some of the land-grant universities, type in saline soils, and they can give you some guidelines of things that you might want to do to try to reduce that salinity or grow salt-tolerant plants. Improving drainage, trying to move some of those salts out through the soil through better drainage is one way to do that. Things to think about if you have high salinity: past manure application can do it. A lot of heavy fertilizer application or high salt fertilizer application could do it. You might look a little again at those sodium values. You might look a little bit at, say, if you're irrigating your irrigation water. If you have a high water table, sometimes those can pull or push salts upward as the water comes up through the soil profile, and then as it evaporates off, it leaves those salts up there on this top surface layer of the soil. In remediating a salinity issue, again, I would check with your land-grant university, but another thing to look at would maybe be take some deeper samples and see if that salinity is all the way through the soil profile or if it's just in a shallow layer. Maybe you might be able to do some tillage to kind of mix it a little deeper and reduce the salinity by kind of watering it down through mixing it with the soil. But again, I'd say check with your land-grant university for some guidelines on what works well in your area for soils that are high in salinity. Hopefully, like the two samples we see here, you're not seeing a lot of salinity, and that's not going to be an issue for you. All right, I think with that we've pretty well gone through all the different aspects of interpreting a soil test analysis. Again, please refer to our website and our library for additional resources and work with your agronomist. These videos are meant to be kind of a broad overview. They're not meant to replace the relationship you have with your agronomist or your fertilizer supplier. You certainly need to work with them. A lot of the information I've presented is in a kind of a broad brushstroke and is not applicable to individual fertilizer products. So you need to look at your individual fertilizer products and those recommendations coming from the manufacturers before you just make application. So thank you for your attention, and we look forward to doing business with you at Midwest Laboratories.